This is going to be a video explaining some of the sections of Chapter 7 that we're going to be missing for class. First off, we want to talk about different types of evidence that we have a chemical change. One of those would be a change in color. So if you notice that what you have at the beginning and what you have at the end are different as far as the color change, that could signal that you have a chemical reaction. Formation of a gas, meaning if you have bubbling and fizzing occurring in your test tube, that's very good evidence of a chemical reaction. If you form a precipitate, which is a solid substance, when you mix two liquids together, that's good evidence of a chemical reaction. And lastly, if you have the test tube getting warm or cold, if there's any change in energy involved, then that's evidence of a chemical reaction. Next, we want to get into talking about some of the mathematical problems that we're going to be solving. And to do that, chemists use a counting term. Some of the counting terms that you're familiar with, we talk about a dozen, and a dozen means 12. In terms of paper, we talk about having a ream of paper, that means 500 sheets. For buying pop, it might be a case, and that's 24 cans. So there's all different kinds of counting units that we use. Now in chemistry, we use one that's called the mole. And a mole is the same number of particles in 12 grams of carbon-12. So it would be if we could take carbon atoms and pile them up on a scale until the scale said 12 grams, and then we counted the number of atoms that were in there, that would tell me how many a mole is. And a mole is 6.02 times 10 to the 23rd atoms of an element. And that number, 6.02 times 10 to the 23rd, is called Avogadro's number. So anytime we have that number of particles, that means that we have a mole of a substance, just like 12 means a dozen. So if we wanted to look at some different kinds of examples, if we have a mole of any element like aluminum or sulfur, that's Avogadro's number of atoms. Now if we're going to look at molecules, so if we have a mole of water, that means that we're going to have that many molecules. Or if we have a mole of this compound, then we have that many molecules. So we have that many atoms if I have a mole of an element, but I have that many molecules if I have a mole of a compound. And if I'm talking about something that's ionic, meaning a metal with a nonmetal, then I have that many formula units in a mole. But any way that I look at it, I always have that many particles that are in a mole. And we can use Avogadro's number as a conversion factor because 1 mole is always 6.02 times 10 to the 23rd particles. I could write that as a conversion factor, 6.02 times 10 to the 23rd particles in 1 mole, or 1 mole is 6.02 times 10 to the 23rd particles. So we're going to be using that to convert between particles and moles. So here's an example. Wants to know how many copper atoms are in half a mole of copper. So if I start out with half a mole of copper, I would want to align my conversion factor so that I had moles on the bottom, and in 1 mole there's going to be Avogadro's number of copper atoms. So I would take 0.5 times Avogadro's number, and then I would round it to 2 significant figures. Since 0.50 has 2 significant figures, I would have 3.0 times 10 to the 23rd copper atoms. Now if I wanted to go backwards, if I wanted to know how many moles of a compound, if I have 2.50 times 10 to the 24th molecules, I'm going to start with my 2.50 times 10 to the 24th molecules, and I'm going to use my conversion factor, but this time I'm going to put molecules on the bottom so that they cancel, and 1 mole on the top. So I'd be taking 2.50 times 10 to the 24th divided by Avogadro's number, and since I had 3 significant figures to start with, I would have 3 in my answer. All right, so here's another example. How many oxygen atoms if I have 0.15 moles of aspirin? Okay, so in this case, I have 0.15 moles of aspirin, and I'm going to put moles on the bottom, and I have Avogadro's number of molecules on the top. So I'm converting between molecules and moles since I have a compound. But now they specifically asked me about oxygen atoms. And I can see that in my compound I have 4 oxygen atoms in each molecule. So I'm going to multiply that by 4 oxygen atoms in one molecule. Molecules would cancel, the moles would cancel, and I would have 3.61 times 10 to the 23rd oxygen atoms. So we've just gone through an example of how to go from moles to atoms, how to go from moles to molecules, and lastly, moles to atoms if I have a compound. Now the next thing that we want to look at is molar mass. And we know how inventive chemists are with their naming, so molar mass is the mass of a mole of one substance. And it is also the same amount of grams that is in the atomic weight. So here's the average atomic weight of silver, 107.9. So that means that my molar mass is 107.9 grams in 1 mole. For carbon, the atomic mass on the periodic table is 12.01, so that means I have 12.01 grams in 1 mole. For sulfur, the average atomic mass is 32.07, so that means I have 32.07 grams in 1 mole. So I know the molar mass of any substance on the periodic table because I know the average atomic mass is given on the periodic table. Now we could also use that in some calculations, because if I wanted to find the molar mass of calcium chloride, then I have to look up the molar mass of calcium. So off the periodic table, here's that average atomic mass. Here's chlorine, I have 2 of them, so I have to take chlorine's average atomic mass, which is 35.453, and I'd be taking it times 2. That gets me the 71, and then I would add those up. And in this case, they're rounding to the nearest decimal. Well, if I wanted to find the molar mass of K3PO4, I would do it the same way. I have 3 moles of potassium in there, so I'd take 3 times potassium's molar mass. And then I have 1 phosphorus, so I look up the average atomic mass of phosphorus and take it times 1. I have 4 moles of oxygen, so I take 4 times oxygen's average atomic mass. That would be here, and then I would just add them all up. So this is telling me how many grams in my molar mass, or how many grams that I have for a mole. So to use that as a conversion factor, if I were to find the molar mass of CH4, it's 16.0 grams. That means there's 16 grams in 1 mole of CH4. So I could write that as a conversion factor. 16 grams is 1 mole, or 1 mole is 16 grams. So you can see we're going to do some conversions with that. So if I have acetic acid and I have 25.8 grams, so I'm going to start with 25.8 grams, and I would like to know how many moles I had, then I would use the molar mass. So I'd have to do 2 carbons, 4 hydrogens, and 2 oxygens, add that up off the periodic table, and that means there's 60 grams, which is what I got for my average molar mass, or for my molar mass, and then I would take that and put it on the bottom so my units would cancel. I take 25.8 times 1 divided by 60. I have 3 significant figures here and 3 here. So to go from grams to moles, I'm dividing by my molar mass. Okay, my second example, I have 0.320 moles. So if I have 0.320 moles and I want to go to grams, I need the molar mass. In this case, I have calcium carbonate. So I'd have 1 calcium, 1 carbon, 3 oxygens, all added up off the periodic table. That's going to get me 100.1. And then I line up my units, so since I have moles here, I would have 1 mole on the bottom, and I would use my 100.1 on the top. I would multiply those 2 numbers. I have 3 significant figures here, so I would have 3 significant figures in my answer. So in this case, if I wanted to go from moles to grams, then I'm multiplying by the molar mass. I call the mole hole. So moles live in the ground, so here I'm going to have my moles. I'm going to put grams on this side, and I'm going to have particles over here. All right, so to go from grams to moles, the conversion factor that I use is the molar mass, which is the thing that we were just looking at where we add up all those average atomic masses from the periodic table. And to go from moles to particles, I'm going to be using Avogadro's number, 6.02 times 10 to the 23rd. Now, anywhere on this chart, if I go down, that means that I'm going to divide. If I go up, then I'm going to multiply. So in this case, I had moles to start with, and I wanted to find grams. So if I go from moles to grams, I'm going to go up the table, up my mole hole. That means I'm going to multiply. So I would take my moles, multiply by my molar mass, and that's going to get me grams, just like I did on this problem. If it was reversed and I started with grams, like I did in the last slide, I would be going down from grams to moles. So if I go down, that means I'd have to take grams divided by the molar mass to get moles. Now, several slides before this, we were using Avogadro's number to go between moles and particles. So if I wanted to go from, let's say, molecules to moles, I would be going down. So I'd take my molecules divided by Avogadro's number to get my moles. If I have moles and I wanted to know molecules, then I'd be going up on my mole hole, and I would take moles times Avogadro's number to get my molecules. So the mole hole may be valuable for you. It's just a reference. You can always line up your units and cancel, but sometimes that's frustrating for some students. So the mole hole might just give you a kind of a pictorial reference to look at. All right, the last thing that we're going to look at is looking at chemical reactions and going from moles of one substance to moles of another. So if I look at a balanced equation, like the one that I have here, that means I can read this as 2 moles of iron react with 3 moles of sulfur to form 1 mole of iron 3 sulfide. So the coefficients that are in here tell me how many moles that I have. And if there isn't a coefficient, that's the same as having a 1 there. So I could write a mole to mole ratio. And what that is that's going to be a ratio between the moles of the substances, and those numbers are going to be from the coefficients. So if I wanted to know between iron and sulfur, so here's iron and here's sulfur, I would have 2 moles of iron for every 3 moles of sulfur, or 3 moles of sulfur for every 2 moles of iron. If I was looking at iron and iron 3 sulfide, then I have 2 of the iron for every 1 of the iron 3 sulfide, or vice versa, 1 over 2. Now if I was going to be looking at sulfur and the iron containing compound, then I would have 3 to 1 or 1 to 3. So the coefficients in a balanced equation enable me to write a mole to mole ratio. So in this case, I have an equation. They want to know how many moles of carbon dioxide, so they want me to find this term. And they want if I have 2.25 moles of C3H8, so this is the one I start with. So I have 2.25 moles of the C3H8. According to my equation, my mole to mole ratio using my coefficients would be 3 moles of carbon dioxide for every 1 mole of C3H8. So my units would cancel and I would have moles. And since I started with 3 significant figures, I'd have 3 significant figures in my answer. Here's another one. So how many moles of iron, so they want me to find iron, if I have 12 moles of oxygen. So I'm going to start with my 12 moles of oxygen, and I'm looking for iron, and according to my equation, there's 4 moles of iron for every 3 moles of oxygen. So 4 moles of iron for every 3 moles of oxygen. I put the oxygen on the bottom, so it'd cancel out with the oxygen over here. And I'd be taking 12 times 4 divided by 3. And since I started with 3 significant figures, I would end with 3 significant figures. Now, if I, let's say, had 12 moles of oxygen, And let's say I wanted to find, in this case, my compound. So I have oxygen and I want to find this one. So I'd put my oxygen on the bottom, 3 moles of oxygen, because there's a 3 for the coefficient. And if I wanted to find the product, there's 2 moles of my Fe2O3. My units would cancel. 12 times 2, which is 24, divided by 3, and I would have 8, 3 significant figures, moles of Fe2O3. So if I want to go from moles of one substance to moles of another substance in a balanced chemical equation, I just need to use my coefficients. And that takes us through some of the kinds of calculations that are going to be expected of us in Chapter 7.